So check out this next example, comes from the multiple choice test from 1985. I have a cone, and the radius and the height of the cone are both increasing at exactly 1/2 of a centimeter per second. The question is, at what rate in cubic centimeters per second is the volume of the cone changing at the exact moment when the height is 9 centimeters and the radius is 6? So, what do I know? I know that, where's my pen here? I know that dr dt, the rate at which the radius is increasing, is 1/2 of a centimeter per second. I also know that dh dt, the height is also changing at that rate, 1/2 centimeter per second. And what have I been asked to find? I've been asked to find, we seek dv dt, the rate of change of the volume at the exact moment when r is 6 and h is 9. So, before I move this, we have to think about what we're going to find. We're going to write an equation, and it's going to have to contain the variables for which we either already know the rate of change or for which we seek the rate of change. So, look, there's a lot. We're going to need an equation that relates r and h and v together. Okay, so I'm going to move the slide and we're going to do that. What equation are we going to write? Well, it's nice that they actually gave us the equation already. We're going to write the equation for the volume of a cone. So here we go. I have an equation that relates v and r and h. I'm going to differentiate both sides with respect to time. No problemo. All right, but this is where this problem becomes, I don't want to say difficult, but at least not trivial. I'm taking the derivative of this equation with respect to time. Time is not one of the variables in the equation, and in fact I have 2 other variables in the equation already. So there's the r, there's the h. So I have r's and h's, but I need to take the derivative with respect to time. This requires the use of the chain rule and the product rule. So we're going to ignore that blue dot, ignore that blue dot. I'm going to think of this as a multiplication problem. I'm going to think of this as a big multiplication sign. When I take the derivative of v, so dv dt, I'm going to use first times derivative of the second plus second times the derivative of the first. Here's my first. So 1/3 pi r squared times the derivative of the second. Well, the derivative of h with respect to time is dh dt. Plus the second, that's h, times the derivative of the first. Well, I'm going to bring the 2 down from the front, and this is going to be 2/3 pi r to the first now, times, I was taking the derivative of an expression with respect to time, and the expression contained the variable r, so this is going to be dr dt. So take that in. It's not trivial. It's not impossible. We certainly used the product rule and the chain rule at the same time before. But that's what they're testing you on this problem, is that you're going to remember to use the product rule even when you're taking a derivative implicitly. Okay, so go back to what we want. We were looking for dv dt, and that's good because we have dv dt in this equation. We're looking for dv dt at the exact moment when h was 9 and r was 6. And we knew that dh dt and dr dt were both 1/2, so watch what happens. So I've replaced dh dt and dr dt, each with 1/2, and I have replaced r with 6 and h with 9, and I can simplify. I would say dv dt at the moment when r is 6 and h is 9 is equal to 24 pi. They already gave me the units in the original problem statement, so I know the units are cubic feet per, do I know? What do I know? Cubic centimeters per second.